In this video, we're continuing our discussion of forced vibrations of damped single degree of freedom systems. So far, we've covered a simple damped spring mass system, including transmissibility and forced vibrations due to a rotating imbalance. And here we're going to consider base excitation in a damped system. So we can consider the response of a damped spring mass system subjected to base excitation. So the forcing function here is on the base instead of on the mass itself. And you see we've got a spring and a damper here. So the free body diagram, mass acceleration diagram, looks like this here. Writing the Newton's law, sum of the forces equals ma, we can see we get this expression. So the force in the spring is minus k x minus y, and the force in the damper is c x dot minus y dot, and our acceleration is mx double dot. So rearranging, we get this expression here, which we can write as this shown here. Now, since we know that y is equal to a sine omega t, then we can rewrite this equation. So you see we've got these two terms on the right-hand side, ky plus cy dot, which we can rewrite in terms of our sine omega t function. So y is ka, or the ky term is ka sine omega t, and the cy dot term is c, and then this is our y dot, a omega cos omega t. So this we can combine these on the right hand side into an r sine omega t minus alpha, basically combining these two into one term, where here r is equal to the magnitude is a square root k squared plus c omega squared, and then alpha is given as is inverse tan. Now let's take a look at this in a little bit further. So this means that the base excitation is equivalent to applying a harmonic force of amplitude r to a mass with a fixed base. So we've already found the steady state solution for such a case. So for the equation of motion, in the case where we'd applied the force directly to the mass, looked like this: mx double dot plus cx dot plus kx is equal to f naught sine omega t. So, and in that case, we had the response is equal to x of t is equal to x sine omega t minus phi, where x was given by this expression and this angle phi was given by this expression. Now for base excitation, this is what we have for our equation of motion, which means that our response is given as the expression here, where this is the amplitude, and then this we've added a new phase angle, which is given as shown here. So let's take a look at these side by side to understand what has happened here. So for the fixed base, we had this equation of motion. For the base excitation, we have this equation of motion. So they look exactly the same, except for on this side. So now instead of f naught, we have this magnitude r, and instead of just an omega t, we've got an omega t minus alpha. So f naught is the same as r. Omega t, instead we've got omega t minus alpha. So this was the response for the fixed base. X of t is x sine omega t minus phi. So now we've got the same thing, x sine omega t minus alpha minus phi 1, where x is the amplitude f naught over the square root term, and in the base excitation our amplitude is r, so that goes in here. And we know r is equal to a square root k squared plus c omega squared. So that means that our x has this form here for the base excitation. Now the omega t ends up in the sine function. Same thing here, the omega t minus alpha ends up in our sine function. And then we've got this, this phase angle. So in the fixed base it was phi, and in base excitation it's phi 1. So the expressions are the same. So we could write the response as x sine omega t minus, let's call it big phi, where we know our expression for x, so we can write x over a as this. And then this big phi is just phi 1 plus alpha. And so that is the combination of these two values here. This form is not convenient, so we can actually rewrite this this phi in this form, and I won't show the details of how you get there, but it can be shown that that is equivalent. So in non-dimensional form, these equations have appear as shown here. So we've got our x over a, which is the amplitude of the mass divided by the amplitude applied to the base, is equal to the square root of 1 plus 2 zeta omega over p squared divided by our square root term. And then the phi phase angle is given as shown here. So this is identical to the transmissibility to the base for a damped system with a forcing function applied to the moving structure. So when we had a fixed base with force applied to the moving structure, we calculated the transmissibility and we ended up with exactly the same expression. So we end up now here, if we're plotting x over a versus omega over p, we get a familiar response diagram for that, and you can see the undamped case as well as what happens when you add damping. So now let's consider the relative motion between the mass and the base. So in what we just did, we considered the absolute response of the mass to harmonic base excitation. But sometimes we can only measure the relative motion between the mass and the base. And so in those cases, we have to infer the absolute motion from these measurements. So in our base excitation case, the relative motion between the mass and the base we can call z. So z of t is equal to x of t, the motion of the mass, minus y of t, which is the motion of the base. So this is the relative motion between the mass and the base. We know, however, that there's a phase difference between x of t and y of t that must be accounted for. So we could use trig identities to solve for this problem, but the easier solution is as follows. So since we know z is equal to x minus y, we can write, we can differentiate this and say z dot is x dot minus y dot, and z double dot is x double dot minus y double dot. And we can rearrange this for x double dot. So the original equation of motion, if we go back to equation 5.23, was written as this. So you see now we've got an x double dot, an x dot minus y dot, and an x minus y in our equation. So we can rewrite this in terms of the z's. So using the previous relations, x double dot we can replace with z double dot plus y double dot, and then we can replace these as well. Or we can write it as this. Since we know that y is equal to a sine omega t, we can find the expression for y double dot. So this, our equation of motion, basically plugging this into here, becomes what we can see here. So now again we've got this familiar left-hand side and a familiar right-hand side where we've got something multiplied by sine omega t. So this we can call our F naught. Again, this equation of motion is identical to that obtained for the forced vibration situation, and it looks quite similar to that of the rotating imbalance that we already considered. So the solution to this problem, we already know, because we've already looked at this, is that z of t is z sine omega t minus phi, where z is our f naught divided by our square root term, or f naught over k divided by our square root term, and the f naught in this case is ma omega squared. So we can write it as shown here. So phi and the phase angle phi is given as this inverse tan. So this is identical to the rotating imbalance situation, except that we have z over a instead of mx over me. Otherwise, the response function looks the same. So again, if we plot this as this response term versus omega over p, we can see what happens in the undamped case as well as when we add various levels of damping. And this relationship, the Z over A, is the ratio of the amplitude of the relative motion to that of the moving base itself. So the relative motion was our Z, and then A was the amplitude of the moving base. So as zeta goes to 0, this equation gives us the same results as the undamped case. And these results can be applied to a variety of vibration measuring instruments. So let's consider a vibrometer or seismometer. So these instruments are large and have soft springs to lower their natural frequencies. So they're usually used in the case where omega over p is much greater than 1. So from the previous figure, we can see that as zeta goes to 0, Z over A goes to 1. So the amplitude of the relative motion between the mass and the base approaches that of the actual motion. Another option for a vibration measurement system is an accelerometer. Now these instruments measure the acceleration levels and tend to be small and stiff with high natural frequencies. So they're used to measure vibrations at frequencies smaller than their own natural frequency, where omega over p is much less than 1. So if omega over p goes to 0, if we think back to our diagram, then Z over A goes to omega over p squared, or Z goes to 1 over p squared A omega squared, where this A omega squared is the magnitude of the acceleration of the base. The amplitude of the relative motion is thus proportional to the acceleration of the base. So to understand the behavior of accelerometers better, we can note from equation 5.34 this relationship here. And this can be rearranged to give that Z is equal to 1 over p squared A omega squared multiplied by this factor. Now, in the case where omega over p is much less than 1, then this term ends up being approximately equal to 1. And then the p squared term is a constant for the accelerometer, since it's the natural frequency of the accelerometer, that is usually determined by calibration. So the factor affects the accuracy of the measurement of the acceleration of A omega squared. So for the cases when omega over p is not 0, this can cause an error because the calibration assumes that this factor is equal to 1. So the farther we get from omega over p equals 0, the more error is introduced into the measurements. So we can see this effect in the accelerometer response on the next slide. So this shows just a zoomed in section of this response versus omega over p. So you can see we're just looking at right around 1 here, and then for very low values of omega over p. This is the undamped case, so zeta is equal to 0. So the error increases rapidly as we approach the natural frequency in the undamped accelerometer situation. So basically, as soon as we kind of get away from here, you can see that this increases, and the farther we get away from 1, the more error is introduced. So this happens quite quickly in an undamped case. Now, if we add damping, this is the undamped line, and these are the different damped lines for different values of damping. So as we add damping, we can improve the accelerometer accuracy for larger ranges of omega over p. So for example, if we look at zeta in the range of 0.65 to 0.7, we can see that we actually get a much bigger range where this factor is close to 1, which means that the accelerometer would be quite accurate in that range. So you can see all the way out to omega over p is 0.4. We're within kind of 1% of the response there, or of the factor being 1. So now let's consider the force transmitted or transmissibility in damped base excitation. So let's refer to the figures that we saw earlier for damped base excitation. So this was the damped base excitation schematic, free body diagram, mass acceleration diagram. So the total force transmitted can be expressed as the force transmitted through the spring and the force transmitted through the damper. And as we defined z as the relative motion, x minus y, we can write this as the force transmitted as kz plus cz dot. And if we think back to the equation of motion that we had, Ft can be replaced by negative mx double dot. So let's see where this came from. So let's compare this and this. So this was equation, the equation we just talked about, and then this was equation that we wrote down before, one of the versions of our equation of motion, 523. We note that Ft is equal to minus mx double dot. And we've already shown for this situation that the response of the mass, x, is equal to x sine omega t minus phi, where x is given by this expression. So the maximum acceleration is basically the maximum x multiplied by omega squared. If you take if we take this and take the derivative of it twice, the amplitude of this would be an x omega squared here. So then, and with this version of x. So the maximum force transmitted is Ft max is m x omega squared, which is given as shown here, and we can rearrange this to basically find that Ft max over Ka is given by this expression. So now we've got an omega over p squared and the square root of 1 plus 2 zeta omega over p squared in the numerator, and then our familiar square root term in the denominator. So here, this represents the transmissibility in the case of base excitation in a damped spring mass system. So the maximum disturbing force is this Ka here. And the maximum force transmitted is our Ft max. So we can see what this plot looks like on the next slide. So this is the relationship, the force transmitted in a damped base excitation versus omega over p. And we can look at, this is the undamped response. So as zeta goes to 0, we recover the undamped response, and then now you can see what happens for different values of the damping ratio of zeta.